The Earth, where our children are born, live and die. The Earth where Homo sapiens emerged from millions of years ago, where civilizations flourish. This lonely planet here, held by forces of gravitation in the vacuum of infinite space, the Earth here is seen 6 billion kilometers away by the Voyager probe, which is today leaving the solar system. The Earth, a pale blue dot. But the Earth is our common village, revealed without any national borders by this image from the mission Apollo 9. This image is probably one of the most reproduced images of all existing images on Earth, more than the Joconde of Leonardo da Vinci. And why? It's because when this image was published, it gave to the humanity the immediate perception, visual perception, that we had a small planet to live in and to protect. And the Earth cities shining at night, which is a fairly recent, less than a century, evidence seen from millions of kilometers away that man is there. This is a child. He is 16 months old, and he is full of curiosity. He explores the light. This light, thanks to which we know the universe we live in. This light coming from the sun to maintain life on Earth. This light which, coming from the most remote galaxies, tells us about the deepest past in time of the world. The questions we have in mind, we all have those questions in mind. The questions which science, philosophy, religions deal with, the questions we have to introduce our students to. Where do we come from? Who are we? Where are we going from? And I take this for more than a mere coincidence that this is the title of this Gauguin painting, which was just painted in Polynesia, which was mentioned by Mrs. Ross a minute ago. Why would this matter for education? Could it help, considering the universe as a whole, to prepare children for the issues they will have to face in their future? And if so, how? These are the questions I would like to address in this lecture, since I was asked to do so. The universe is a topic which may seem quite remote from this summer week. And I'm very grateful to Courtney Ross and to the organizers for having considered that the great story, the story I'm going to tell now, deserved to introduce, it's quite an honor for me too, our conversations of the week. And here is the steps I'm conveying to. I would like first to take some perspective to go back just 1 century ago, 1900. What did we know about the universe in 1900? And then there was this fantastic century of discoveries. What do we know in 2000, at the beginning of the 21st century? And after this landscape, which of course I will have to keep short because one could speak for hours and days on this topic, I will move in the second part of my talk to the way this great story could irrigate education. So let's look at 1900. what did we know? We knew that 7 planets were orbiting around the Sun. We knew that we had one star, the Sun, which was similar to the millions of stars seen in the sky. We didn't know at all where the Sun was taking its energy from. The idea is that it was burning like coal or glowing like metal, heated liquid metal, were not standing up properly. So where did the energy of the Sun come from? And where was the energy of all stars coming from? This was completely unknown. We only knew one galaxy, ours, with millions of stars, billions of stars. What was beyond this galaxy? One knew the size of the galaxy, about, in light years, about 30,000 light years from radius. One approximately knew the shape of the galaxy, flattened pancake, but beyond, vacuum, infinity, other objects, island universe, as Immanuel Kant named them without knowing them at all, just as a guess. Complete ignorance. And the Earth. Of course, the Earth was better known, it had been explored, but one had a very poor idea of the age of the Earth. There was a lower limit of this age thanks to the computation of sediments, which were giving at least tens of millions of years, but how much more? One knew very little about the continents and their stability in time. The idea of continent drift and tectonic plates was just beginning to emerge, but not substantiated yet at all. And finally, again, the question of the formation of the Earth, where did the Earth come from, was a complete open question. A French famous scientist, Pierre Simon de Laplace, had proposed an hypothesis to form the Earth and, in fact, the whole solar system from a collapsing cloud of matter, which he called the primitive nebula. This was written in 1795, but it was not substantiated by any evidence yet, or any direct evidence, should I say. So there was at least one triumph, which was the celestial mechanics, which was introduced by Newton at the 18th century, and which was proven through the force of gravitation to organize the whole known universe, the galaxy itself, the motion of stars in the galaxy, with the self-gravitation, the motion of planets around the Sun, the motion of comets coming and disappearing, etc., and the accuracy of those predictions were a triumph for mathematics and for a mathematical description of the world with classical physics. But still, as I briefly said, questions remained. And of course, science is much more questions than answers. So in a sense, the time was ripe to open this new century of discoveries. Those were the planets of the solar system I just mentioned with the size. You know, I masked the last one, Neptune, because it was not discovered yet. It was discovered in 1937 in Flagstaff by Percival Lowell. And the other planets were all known by the Greeks with their naked eye observations of the sky. So also celestial mechanics describe much better their motion. The discovery of novelty in the solar system were at that time rather poor. And in fact, all those planets were essentially dots on photographic plates showing absolutely no details. And when some details were drawn by astronomers with maybe a little bit too much imagination, like the astronomer Schiaparelli, drawing from his visual observations of the planet Mars, canals on Mars, which indeed produced a lot of public interest about Martian people drawing canals to irrigate their planets. All that proved wrong because the quality of images given by the refractors at that time was very poor. So all the details which you see on those planetary images, in fact, are modern details. They were not available at that time. I also mentioned the galaxy. This is the Milky Way, seen again, there's too much light in the room. That's the problem with astronomy. You have to have darkness to see it. Well, if there were less light, you would see, you barely see them, the two Magellanic clouds on the bottom left, which we know today are galaxies, are companion of our own galaxy. But at that time, they were called nebula, and no one knew if they were simply not clouds of gas like the other clouds marking the dark areas in the Milky Way. So all two stars were properly understood by spectroscopy in the 19th century for their composition. The structure of the universe beyond the Milky Way was entirely not even known, not to say understood. Well, let's continue briefly with this enumeration of 1900. There were positive things. One fundamental point which came during the 19th century was that the atomic elements which chemists discovered progressively on Earth, some were known since a long time, but oxygen was discovered by Lavoisier at the end of the 18th century. Hydrogen was known, but iron, copper, sulfur, etc., etc. This was organized in the famous table of Mendeleev at the end of the 19th century, and spectroscopy discovered that those elements were present everywhere in the universe with the same properties. And this was a fundamental discovery that the universe is homogeneous. We are not in a special place with special elements which would be different in other places. Their relative quantity, what the astronomers call abundances, may be different from place to place for reasons of evolution, but they are universal. This was a very fundamental point on universality. The second major discovery at the end of the 19th century was that light had a finite velocity. Now, the fact it had a finite velocity was known since a long time, since the Danish astronomer Rømer at Paris observatories in 1666 demonstrated by observing the satellites of Jupiter that light had a finite velocity. But he was not able to measure this velocity because he didn't know the size of the solar system at that time with sufficient accuracy. But this velocity was measured all along the 19th century by people like Fizeau and Foucault. This was known. And this had another fundamental consequence, is that given the huge distances which were known, I mentioned 30,000 light years for the size of our galaxy, that when we see far away, we see in space, we also see far away in time. And that this is an unbreakable limit to our knowledge of the distant stars and other objects in the universe. When the light comes to us, it comes after a long journey which took a long time, and we don't see them at the given instant of observation. This was the questioning of simultaneity of observation which led Einstein to special relativity. There was a pending question among the questions I mentioned, which is, what is the vacuum between stars made of? Vacuum means lack of matter. But does it mean that there is nothing in the sense of an absolute nothing, a kind of metaphysical nothing in this vacuum? it couldn't be, because light moves in that. So how does light move? Does it propagate by vibrations of something? This something was called ether, and this ether was disproven at the beginning of the 20th century by relativity not to exist. Opening again a question which is still a question today: what is really vacuum? And finally, and I could make the list longer, of course, this very important dispute about life, which happened at the end of 19th century. And in the proceedings of the French Academy of Science, the dispute between Louis Pasteur and his opponents about the question, does life proceed from nothing, or does life proceed from life? Of course, Pasteur was defending the second opinion. Many people were defending the first one. And Pasteur demonstrated with strong scientific evidence that life was proceeding from life, which opened the way, of course, to the analysis of generation and then further genetic analysis much later on. But what was life? This was a complete unknown at the time. So this is the opening, in a sense, of this 20th century history. Now, I would retain three ideas for this achievements of the last century. The first one is that the universe is most likely infinite, and it's in evolution, in a constant change. And this evolution has begun, as far as we can tell, which doesn't mean that it's the real beginning of things, about 13.7 billion years ago. The second idea is that the Earth is an interesting place because we live in, but it's one of millions and maybe billions of planets orbiting other stars, either in our galaxy or in other galaxies. So this is a shake-up which may be comparable or probably even much stronger than the shake-up which happened with the Copernic vision that the Earth was not the center of the solar system, but the sun, he thought at the time. And then the third point is that life remains an enigma. We know more about life, but life in the universe is still a completely open question. So I will now move along those 3 points. First, the universe is in evolution. We know today there are billions of galaxies. Remember, a century ago there was one, ours. Billions of galaxies spread over space to very large distances. But I repeat, we don't see the universe at large distance as it is today, assuming that this has a meaningful sense to have this kind of God's view of the universe. I mean, not being inside it, but trying to see it globally. Each of those galaxies has billions of stars, and each of those stars have maybe 1, maybe 5, maybe 10 planets. I will come back to the planet later. So if we take a galaxy like this one, which is very similar to ours, our sun would be about at the position marked. And you see the size is about 30,000 light years in radius. This galaxy has shapes, motions, gas, stars, collisions, etc., etc. This is full of details, but I'm not going in those details. The main point there is that all what you see here is hydrogen. This glowing gas that we receive the light from is hydrogen. There are other elements in small quantities, helium and carbon, sulfur, nitrogen, oxygen, etc., in small proportion. 1 part in 1,000, in 10,000, in 100,000. So the universe, that's hydrogen. This is another view given by the Hubble Space Telescope of the distant universe. On this picture, which was famous, after it was taken, you see not a single star. Every dot you see is a galaxy. So every dot is a billion of stars, or 10 billion, or 100 billion, more typically 100 billion of stars. You can guess the shapes. You see some are elliptical, some are spiral, some are irregular. The galaxies have their own history, and they are different. We know their age, billions of years, very comparable at the age of our galaxy. Another fundamental point is that we have had, in the course of the development of general relativity in this 20th century, to depart from the very overwhelmingly simple vision that light propagates in straight line, and that if we make a triangle with 3 of those straight lines, say 3 stars forming a triangle, the sum of the angles of this triangle would be 180 degrees. That's what we call Euclidean geometry. But that's not the geometry of the universe, because the space is curved by the masses, by the matter. And to use the very nice sentence of Edmund Wheeler, when he was professor at Princeton, he said the matter tells to the light how to curve its path, and the light tells the matter how to move, or not the light, but the curvature tells the matter how to move. So the matter tells the space how to curve, I should say better, and the space tells the curvature of the space tells the matter how to move. This is showing, in a nice sentence, the intimate connection that Einstein demonstrated in 1916 between the geometry of the universe, the curvature, the lines, the angles between those lines, and the content of matter and energy, should I say, because we know that matter and energy exchange themselves according to the Einstein law, E equal mc squared. So this matter tells the geometry, and the geometry tells the motion of matter. And this is this image is a beautiful demonstration of this curvature effect. We have in the foreground a number of galaxies. Again, no stars there, only galaxies. And in the background, but you don't see it, we have one galaxy. And this galaxy happens, by accident, to be aligned for us, observers, with the foreground galaxies. So we have aligned the background galaxy, the foreground, they are about halfway, and us. And the light coming from the background galaxy is curved by the cluster of the galaxies in the middle of the path, and then it's bent back to us observers. And we see an aberrated image of this background galaxy. And this is the kind of, this sort of slopey shape you have in the bottom. And in fact, this aberration is so clear in a sense that it respects some of the shape of the galaxy. It's like you were looking at this background galaxy with a kind of irregular magnifier. Not a very nice magnifier, but irregular, which would give a fuzzy image. And you can see some of the spiral arms on the bottom and even some of the stars, blue-looking points. So this is a magnificent demonstration on a local situation that the universe is curved. But this curvature, in fact, is a fundamental ingredient of today's cosmology. Now, those galaxies have not existed forever. And the stars they contain have not existed forever. And the elements which are contained in those stars, helium and even hydrogen, carbon, oxygen, have not existed forever. This is why I said the first fundamental result of 19th century science was to understand that universe was in evolution. This is very contrary to the vision that Newton had, where the universe was perpetual. I mean, motion of planets in the vacuum were frictionless. For Kepler, a century before, this was impossible to think the planets moving in vacuum. So he assumed that the planets were supported by spheres of glass, but so nicely made glass, so transparent, that no one would see the glass, and we would only see the planets. Now, Newton was not accepting this idea. The planets were just moving in vacuum, pulled by gravitation, but still their motion was forever. No idea of evolution. So, question came. What was before the galaxies were formed? It's a very difficult question because we don't see this time. We don't see the light coming from this period. But one can simulate because we know the law of nature which control the physics of it. And with powerful computers of today, one can put all the ingredients, all the atoms, in limited numbers of course, to simulate what, with the existing and known laws of nature, the universe would have done at this period of time. And this is an example of this simulation. I could show you a movie, but it takes a lot of memory in computer, so I have only a picture. You see, the bright points are matter, not glowing, as I said, but and the intensity is just representing in blue the temperature, and the green is the density. Oh, you don't see the green too well. Okay. So what we see is that from a universe uniformly filled with hydrogen, very uniform filling, no blobs, no stars, no galaxies, then gravitation will, self-gravitation of this matter will organize the matter along long filaments. And at the intersection of those filaments, then the density would increase, and of course it's a self-propagating phenomenon, and then the galaxies would form. This would have happened about 12 billion years ago, during the Dark Age. So today, we have a reasonably grand scheme for the formation of galaxies, not of the details. One of the problems which comes into this pattern is that we know ordinary matter, those atoms I was speaking of, but one has discovered, and the initial discovery of that is 1937 by Fred Whipple, but it was not taken very seriously until the 1970s, that on top of this ordinary matter, which is called baryonic matter, because the particles it's made of are baryons, which simply mean heavy particles, then there is another kind of matter, which is called dark matter. Now, it's dark for several reasons. It's dark because we don't see it, but it's also dark because we don't at all understand what it is. We only have evidence of the existence of this dark matter because of its gravitational pull, which is measurable on stars. Now, in this room, there is dark matter, but we don't see it, and we don't experience its gravitational pull because of its uniform repartition. It's only at large scales, galaxy scales, that the repartition becomes sufficiently inhomogeneous for the gravitational effects to be perceptible and measurable. And this matter exists because it's impossible to obtain such a simulation of the galaxy formation process without adding in the computer as an ingredient dark matter with its gravitational properties. And you see that the red, again, you would need, you have little red dots there, which are the amount of dark matter which has to be put into the model for the model to converge toward a realistic description of galaxy formation. Okay. So this is a grandiose evolution, and I should add that we started from hydrogen. And today we have all those atoms, those 100 or so elements of the Mendeleev table. Where do they come from? This is the role of nucleosynthesis or matter evolution, another type of evolution, which is chemical evolution, or nuclear evolution, would it be better to say, where in the nuclear furnace of stars, fusion of hydrogen into helium, then helium into carbon, then carbon into higher mass elements, produces those heavy nuclei of matter. Generation after generation, the stars produce more carbon, more oxygen, etc. And the universe is enriched in heavy elements. So this mechanism was part of the explanation of the energy of stars. The point I said was unknown in 1900. And Hans Bethe got the Nobel Prize for his discovery of this, and of course making it quantitative, explaining that why we receive from the sun 10 to the 26 watts or joule per second from the production of energy in the heart of the sun. And of course, once it was demonstrated for the sun, it was also demonstrated for all the billions of stars of our galaxy and other galaxies. So, evolution from a uniform universe full of hydrogen, forming galaxies, forming stars, forming elements, and forming planets. We'll come back to this. But what about before that? Can we go back in time again? And this is the great achievement of what is called the Standard Model in the last 50 years or so, which describes the universe as a whole in its earlier time. And I am careful not using the word beginning or origin, because what physics describes is transformations. And we transform hydrogen into carbon. We transform a cloud into a star, etc. But the absolute beginning of things, physics doesn't really know what it is. So what we describe is a universe in expansion. Those galaxies, and that's interesting, they were identified in the 1920s, where theoreticians using general relativity and special relativity, the two great achievements of Einstein in the previous years, said that the universe must have been different in the past as it was observed today, and said that the universe must be expanding, which was quite contrary to Einstein's ideas. Later he said that his refusal of this idea of the expansion of the universe was the biggest mistake he had made in his scientific life. So the theoretician came to the conclusion that the universe must be expanding. And the law of this expansion, which we call today Hubble Law, because Edwin Hubble at the Mount Wilson Observatory above Pasadena discovered it by observing galaxies, the Hubble Law should in reality be called, and it will probably be soon called, the Lemaitre Hubble Law, because Lemaitre was a theoretician who, on the basis of general relativity, had predicted the expansion of the universe 2 years, 1927, before Hubble discovered it by the observations. So as often in physics, you have a convergence of the ideas, the theory, and the evidence which comes from experiment or observation. So this universe is an expansion. We know that this expansion began at least 13.7 billion years ago. This is the horizontal axis here. We know that this expansion at the beginning slowed down. So once the galaxies were moving away from each other, the velocity decreased. This is similar for same reasons, actually, that a stone you send above you, and then, of course, the velocity of the stone will decrease with the altitude because its energy will be used to fight against the gravity. So it's during this period of expansion, early expansion, that the galaxies formed. We have learned only recently, 1998, that this expansion is now accelerating. This is a great discovery which gave the Nobel Prize to the 3 discoverers of it. And it was made observing supernovae, exploding stars. I will not go into detail on that. But it challenged the physicists. What is the cause of this acceleration? And again, it's a big unknown of today, science, and it was again called dark, but dark matter is already taken, so it's dark energy. There is something in the universe which is a pull, in a sense, which pulls the vacuum to expand faster than gravitation only would produce on galaxies. This dark energy is one of today's big questions of physics. So you see, maybe 2100, there will be a long list of questions being solved. But there is another important result, which is describing what happens very close to the left part of this graph, is that the universe, as we see it today, has several mysteries. One of them is the following. If one looks at 2 different directions, on details on the structure of the universe, we see them essentially identical. That's called the homogeneity of the universe. It's homogeneous. There must be a cause for this homogeneity. It cannot be just by accident or coincidence. And a cause means that those 2 regions of the universe must have been able in the past to, in a sense, speak to each other, to exchange information. But information can only be exchanged at the velocity of light. This is a fundamental law of physics. Those 2 parts in 2 different directions are too remote and have always been too remote in the past to have been able to exchange information. Then, why can they be so identical? This is a paradox which can only be solved by a conceptual vision of the beginning of the expansion of the universe, which is called inflation, an idea which was introduced in the 1980s by Paul Guth. And this inflation was an hypothesis until very recently observations of this remote hydrogen time showed that the universe, as observed like that, and I'll show you the graph in a minute, has the imprints, not direct, but the, in a sense, fossil imprints of this period of inflation. So the description of the evolution of the universe, to be brief and short, maybe a little bit schematic, is today made of three parts. One, exponential growth of something which was not hydrogen, because temperature was much too high for hydrogen to subsist. It was made of elementary particles, not even of protons and neutrons, because they were unstable at that temperature, but of quarks, the basic constituents of matter. The second part was the expansion controlled by gravitation. And the third part is the accelerated expansion, which is controlled in part by dark matter. And along this long path of 13.7 billion years, and we give this time because we don't know what was happening before, and we don't even know what are the physical laws which were applying in those particular conditions of the universe, then electrons, protons, neutrons, hydrogen atoms, helium atoms, carbon atoms, and then finally molecules were formed. See, this is the way we investigate this remote past. I said that during the Dark Age there was no light emitted, so it was dark really, but before the Dark Age there was a moment where protons and electrons recombine to form hydrogen atoms. And at this moment, some light was emitted. And we can receive this light today. It has traveled so long that due to the expansion, although it was emitted in blue and red color, today it's radio waves. It has been shifted to the radio waves. So this is a picture, or those are successive pictures with more and more details. The first one was obtained by a NASA satellite, Kobe, 20 years ago. It was very fundamental because it showed that on this uniform background of light produced by hydrogen, a homogeneous universe, there were some fluctuations, very minor. They are amplified in this graph, which were the seeds of galaxies, and they are the seeds which the computer model produced. You can see in the lower image that the resolution is much better. This map was obtained with a balloon flight. And then finally with a satellite, which was a difficult venture, a European venture this time. The two previous ones were from the US. This is the Planck mission, which was just finished 2 years ago, and which gave an even more detailed of the map of this universe. And on this map, here is the proof of the existence of the inflation of the universe. Well, so much for the first topic. The second one is exoplanets. So this was the grand universe, you know, difficult physics and so on. Now, exoplanets is completely different. In October 1995, a search which started 25 centuries ago for other worlds, because there are traces in Democritus publications and in Lucrece, of course, in De Natura Rerum, discussion, do other worlds exist? Do other planets exist? Finally, the first exoplanet, or they are named, was found around another star. This was found by a Swiss team, Michel Mayor and Didier Queloz, and on a French observatory in southern France in Provence. Now, we are in August 2014. I checked last night on the compilation of exoplanets. We know in our galaxy, all those exoplanets are known in our galaxy, because for other galaxies, it's too far away. It's too difficult today to find them. We have 1815. This is the date of the Treaty of Vienne, which reshaped Europe after Napoleonic Wars, but I don't think it has anything to do with it. But it's a good way to remember. And those are around 1130 stars, which immediately means that there are many stars who have more than one planet. They have been discovered by various methods. I pass on that. This is an interesting one because it was the very first planet discovered by one of my colleagues, who is Daniel Rouen and his co-workers. He is now the president of the Pâte Fondation, with Space Observatory Corot. This is not a photograph, it's an artist view. This planet is not too far away, it's at 500 light years, so it's not too big distance, and it's only 5 times the mass of the Earth. So it's a rocky planet, it's not a gas planet like Jupiter. A similar mission, more ambitious, of NASA, which is still in orbit, which is called Kepler, today has discovered a multiple system. This is again an artist graph of this system. It's a little bit further away, slightly over 1,000 light years. And you see there are 7 planets orbiting this star. Another interesting case is the closest star of the Earth is called Proxima Centauri. It's 4.5 light years. So it's almost a distance where you can think that in some remote future, a space mission could go not with men, but with maybe small webcams and travel for maybe a century and shot in close the planet. Near Proxima Centauri, there is the star, the beautiful star in the southern sky, Alpha Centauri, and this has a planet, which is very close to the mass of the Earth, 1.4 times the mass of the Earth. I'll just show this one, which is another very interesting system, Kepler 186, which was recently discovered, was published this year. And you see now the comparison between the Earth and Kepler 186, one of the planets, F, which is called 186F. Of course, the surface is a guess. I mean, no one has observed or photographed the surface of this planet. But if you compare the size of the two systems, our solar system with its planets and Kepler, you see it's really in the same ballpark. And this has a very important consequence for the future analysis of exoplanets, is that we have this concept of habitable zone. Not inhabited, but habitable. What does that mean? It means that if you have a star of a certain brightness, and this is the ordinate of this graph, then this star would have, if we have a planet orbiting this star, depending on the distance, water on this planet would be freezing if it's far away, would be liquid if it's closer, or would be in vapor if it's even closer. So the Earth is in this narrow range, which is this red track that you see, green track, excuse me, that you see, where water for a given brightness of the star would remain liquid. Which means that it's most likely the conditions for the emergence of life. So scientists today are very interested in finding exoplanets which are located around their stars in this habitable zone, because that's where the future search for life would have to be done. That's where we stand. If you take the time span, this is 20 years since the first discovery, and we have about 22,000 exoplanets. We have enough to make statistics which indicate that a substantial fraction of stars in the galaxy have planets, maybe 5%, which if you take 100 billion of stars in our galaxy, you see the number of planets. Now, how many of those are looking like the Earth, are rockies with a solid surface? How many do stay in the habitable zone? Do they stay long enough in the habitable zone despite gravitational perturbations that the evolution of pre-biotic, pre-life chemistry could lead to life, all those are open questions. And those are probably among the most fascinating questions for 21st century science. Okay, after this kind of panorama, I would like to move to education. The discovery of this century, as I presented them, they unveil a long story. This story was untold by everyone until humans began to decipher and communicate it. The story reached today a broad public, but too often in a superficial and sensational manner. Indeed, the creation of the world or the possible existence of other worlds had been the subject of myth in many cultures, reflecting the questions that we humans, when facing natural phenomena, were asking, and our attempts to answer them. And in this sense, the myths are the very beginning of science, and they should be respected rather than despised for being primitive or childish stories. The great story of the universe, told today by our scientific knowledge, prolongs, in a sense, the myth. It plunges in this remote past and describes the successive steps, as I have tried to do it very briefly today, through which emerged ordinary matter, complex molecules, local apparition of negative entropy, which means order and organization in opposition to chaos and disorder, and then stars, planetary systems. The Earth is one of these millions of planets, and on this Earth we begin to know how the process of this continued evolution occurred and gave birth to life at least 3.5 billion years ago, since through the stromatolites, the fossils, we have evidence of production of organic matter, at least during this time. This is through a not yet deciphered process, the apparition of life, of which we don't know at the moment any other example. And life itself evolved and gave birth to humans in a continuous process, which is also being progressively described by anthropologists, even if not perfectly understood. And although I use the word continuous to mark that each step of the process is rooted in the previous stage, I use the word transformation, caution must be exercised there. The process, this great story, is full of ruptures, bifurcations, unpredictable events, each one introducing novelties. Humanity and humans are born from such transitions. Cultures are a legacy of this distant past, and they continue to experience such bifurcations. Learning and understanding history and geography, this is part of education. We all think that. What is new today is that history does no longer start with the Egyptians, or even with the emergence of Homo sapiens in Africa, as we will hear in a moment. It began 13 billion years ago. Space is not limited to the surface of the Earth, not even to the solar system. It expands at infinity. Geography should be renamed cosmography. To understand the present and to prepare for the future, education can no longer ignore the great story. This is my vision, at least, to answer your questions. And I want, therefore, to examine briefly on 4 topics, how and where the great story can impact education. First, man emerging from nature. The great story must be told with enthusiasm and admiration, but also with care and humility, far from becoming a dogma. As a global vision of universe history, it represents our knowledge of today, but yet it is full of unknowns and questions, and I've tried to give example of that, to the point that this lecture, if given in 2100, would probably appear naive and ignorant in many respects. But the most important consequence of what we know today is as follows. The whole humanity is a species. Each society and culture as a group of humans, each human as an absolutely unique person, all are deeply related to the whole universe, progressively unfolding to knowledge. This relation is not only conceptual and cultural, it is physical. As for example, in the body of any one of us, about half of the hydrogen atoms contained in water molecules have been one day or another in a star. We are cinder, ashes of stars. The relation is physical in the sense that the laws governing the organization of the universe, of matter, even if we don't know where these laws come from or what explains their universality and stability, those same laws are also governing the functioning of our brain, hence our mind, after having governed the evolution on Earth. In the Middle Age, there was a vision of the microcosm reflecting the macrocosm. And this vision, also not scientifically founded in the modern sense, was, I think, intuitively expressing this reality. You find traces of that in the writings of Hildegard de Bingen, for instance, in the 12th century, or in Paracelsus in the 16th century. Traces of the remote past told by the great story are as present in ourselves as the volume of our brain or the memory of trenches during World War I, at a short distance in history. The second point is man discovering and understanding nature. The elaboration of the great story took centuries through a careful construction of cumulative culture. This was so well summarized by Bernard de Chartres in the 12th century, when he explained that we are dwarfs, only seeing far away because we are on the shoulders of giants. This metaphor was made famous by Newton, who adopted it. Dwarf humans, with their short lifetime, their limited mind, and their poor technical tools, but equipped with agile hands, curiosity, and reason, those dwarfs have been able to measure the shape and the size of the Earth only with geometry and shadows 25 centuries ago. Able to establish that planets were moving on ellipses and not on circles, Tycho Brahe and Kepler. To decide that the moon was constantly falling on Earth and that the law of this fall were universal, applying to all massive bodies in the universe, an incredible extrapolation by Newton. To estimate the age of the Earth by looking at geological sediments. To understand why the sky at night was dark and not as bright as the surface of the star, what is called the paradox de Chezeaux-Holbers, only solved after a genial intuition for Edgar Allan Poe by modern cosmology. To realize, I made this point, that hydrogen, carbon, iron were present everywhere in the universe, absolutely identical to the ones we know on Earth. What a legacy of proudness and trust to transmit to young students. Mathematics, physics, chemistry, biology are indeed specialized disciplines taught in secondary school, each one making sense by itself and exploring nature with its specific methods. Sometimes, I'm sure not in Ross School, but in other places I know of, students find the sciences boring, and they even question their usefulness. But how more those sciences become attractive when they are understood as providing critical pieces allowing to understand and to accept the great story. How fascinating then appears their historical development. My third point is beauty, mystery, philosophy. The understanding of the universe is indeed mere science, and great care should be exercised in presenting this science to avoid conclusions which would go beyond what science can prove is based on evidence, reasoning, observations, argumentations, and the construction of an always revisable consensus. Education has always aimed at transmitting elements of truth and criteria to establish truth by an acute judgment or discernment. When education departs from this attitude, it becomes propaganda or dogmatism. But this is not to say that science is the only modality of thought. This would be scientism. Beauty, emotion, is always present in the great story. It begins with the magnificent spectacle of stars in the Milky Way in the dark night. And of course, what was on the screen is a very poor representation of what you would probably experience yourself if you go in a dark night outside of a city. It continues the images of galaxies, the cloud of gas, the unfolding tails of comets, the erupting surface of the sun. This is a cloud of gas, Helix Nebula. What a beauty. This is another cloud of gas forming stars and planets, the Eagle Nebula. This is beautiful. This beauty has deeper emotional resonances when each of these images not only is aesthetically pleasant, but finds its place in a chapter of the great story, when science and aesthetics become tied. Education cannot succeed if not calling for emotion. And too often, science is received as a frozen or even freezing knowledge. Emotion in front of beauty leads to mystery, so well expressed by the questions in the Gauguin's painting. Science unveils many of the mysteries of the world and rightly aims to do so and to continue to do so. Yet, its achievement only stimulates further the sense of mystery. And I would quote Einstein, who in a famous passage was writing, "The most beautiful thing we can experience is the mysterious. It is the source of all true art and science." The insight into the mystery of life has also given rise to religion. To know what is impenetrable to us really exists, this knowledge, this feeling is at the center of true religiousness. And Richard Feynman from Caltech tells a story. The story happens before World War II. A man named Hans looks at the night sky with a woman of his friends. "How beautiful," she says, "and what a mystery." He answers, "It's very beautiful, and regarding the mystery, I may today be the only person who knows why they shine." The man was Hans Bethe. I mentioned his name before. He got the Nobel Prize in 1967 for having discovered that hydrogen nuclear fusion causes the sun and the stars to shine. Mystery for the lady, science for the man, but science only placing further the mystery. Staying here away from religion, I like nevertheless to underline how the great story is an introduction to metaphysics, hence to philosophy, which is a fundamental ingredient in education. Why is there something rather than nothing? What is the difference between the physical, chemical, biological, cultural transformations and emergences as we observe them in the universe, as deep as science can reconstruct the past, and the creation from nothing the coming into being. What could be the meaning of an origin of time? If time began, how could one speak of a before this instant? The laws of nature, this limited number of laws which describes the behavior of matter, of space, of energy, the laws of general relativity, the Schrödinger equation in mechanical quantics. Those laws show that those laws, which are fundamental to establish the great story, they show that there exists a universal order behind the appearances which we measure, which we observe. This universal order is so deep, so flexible, that it appears at all levels of knowledge. The apparent shape of the laws may change when explored deeper, but the order remains. It is an evidence which surpasses the human mind and the human existence. What are these laws? Where are they coming from? How could it be that they are so stable and that, in a sense, above the appearances of the universe? How beautiful, would Hans say. We don't know that, but this is coming into metaphysics and philosophy. And my last point would be fragile Earth. And I don't have to develop this very much because it will be developed all along. Let's just remember that in a poetic and dramatic manner, the book of Revelation in the Bible describes an end to our Earth. The Apocalypse of John says the sun became black as sackcloth made of hair, and the whole moon became as blood. It's the sky, the stars fell from the sky, etc. As for centuries, potential cosmic catastrophes were haunting human minds. Collision with an asteroid, contamination by a comet, 1910, extinction or explosion of the sun. Science has relaxed the risk of such events to the point that today, meteorites are tracked to predict and avoid damaging collisions with Earth. The stable lifetime of our sun is estimated to several billions of years. The orientation of the Earth's rotation axis is stabilized for the same period of time by the presence of the moon, etc. The physical conditions on Earth appear to be very robust over time. This planet is ours for a long period. The solar system is ours for exploration for a long period. A certain confidence can reign on the legacy we have received. But the entirely new phenomenon is the impact which humans begin to have on their physical conditions of the Earth through anthropic modifications. And this is why today education cannot be based on a fear for likely catastrophes, apocalyptic events. It has to call for reason. Science education, and for possible action, engineering education. It also has to establish hope and confidence in human destiny and brotherhood. This is a difficult task where moral, ethical, and spiritual values, to also be fostered by education, play a role which cannot be carried by science. I will conclude by saying that the great story is not written once forever, and education must also teach humility and openness. We know for sure, at least from our science of today, that those new worlds, the exoplanets, will remain out of reach forever, not visitable by artifacts, as the robot Curiosity is exploring today the surface of Mars. Those results from the great story will not help us shaping our future on Earth, but their knowledge, progressively acquired by science, will enrich the great story with new chapters which may manifest even deeper the cosmic connections of man. Thank you.